Hi, my name is John Poulter. I'm a master's student in the Atlas Institute CTD program. I came to CU Boulder with a background in electrical engineering and a lot of experience with automation and electromechanical systems. I decided to pursue my master's degree because I'm very interested in robotics, specifically how they can be used for rehabilitation and mobility assistance. Robotic exoskeletons are an excellent example of this. They can be used to restore mobility to users who have suffered some form of spinal cord injury. When I tell anyone that I'm studying robotics, they inevitably ask me how I'll react when machines take over the world. They're usually at least pretending to be joking, but the fact remains that a lot of people see technology as something to be fearful of. I take a much more optimistic position. To me, technology provides solutions to drastically improve the quality of people's lives. Worldwide, there are 250,000 to 500,000 spinal cord injuries a year, with up to 40% of these resulting in partial or complete paraplegia. Exoskeletons have been developed to restore mobility to those who have suffered such an injury. Problem being they are prohibitively expensive, with most costing around $80,000. I want to combine my experience with microcontrollers, circuit design, and 3D design to create a more affordable option. I have created an assistive robotic knee brace that can be used by a person who still has mobility but needs a little bit of help getting around. Last year, I undertook an independent study where I performed a survey of lower body robotic exoskeletons. During my research, I learned a lot about the control systems and actuation used in the industry today. Actuation has been achieved through pneumatic, hydraulic, and series elastic actuators, as well as electrical motors and pneumatic muscles. Electrophysiological sensors are the most common method of control, encompassing electromyography, electroencephalography, electrocorticography, and intracortical electrodes. Of these techniques, only electromyography and electroencephalography can be performed non-invasively. The brace I designed consisted of 7 main components: a store-bought knee brace, a set of 3D printed brackets, 2 electric linear actuators, 2 electromyography sensors, 6 limit switches, a microcontroller, and a battery to power the actuators. The electric linear actuators are mounted to either side of the store-bought brace via custom-designed 3D printed brackets. These actuators are powered by an external battery, and commands are sent to a motor driver board to control the direction of their movement. Retracting the actuators causes the brace to bend, whereas extending the actuators causes the brace to straighten. Limit switches are attached to strategic points on the brace so that they are triggered when the braces reach full extension or full retraction. This stops the motion of the actuators to prevent damage to the system and the person using it. The electromyography sensors are attached to the leg using adhesive electrodes. One is attached to the quadricep and one is attached to the hamstring. These sensors are able to detect electrical activity in the muscles. An average of the 20 most recent readings from each sensor is calculated, and using this average helps to smooth the input and prevent erroneous spikes from influencing the control system. A threshold has been set for each sensor, above which the muscle is considered to have been activated. When the quadricep is activated, the actuators extend. When the hamstring is activated, the actuators retract. With this control system, a person can regain the use of their knee as if they had never lost mobility in the first place. I achieved my goal of creating a more affordable assistive device. Functionally, my brace is able to do everything I set out to do. As far as price, the cost of parts, and assuming I was paid well for my time developing it, the final product cost less than $10,000, which is approximately $70,000 less than exoskeletons currently on the market. Moving forward, I would like to replace the store-bought brace with a custom-designed one. This would improve durability and eliminate the need for retrofitted 3D printed brackets. I would also like to develop similar systems for assisting other joints such as hips, elbows, and shoulders. With multiple systems built, I would like to introduce modularity, allowing multiple devices to be combined depending on the specific needs of the individual. With this plan, my skills in robotics and design allow me to create novel, affordable, assistive devices to improve quality of life for people whose mobility has been